First speaker is Richard Fletcher from MIT, Acoustic Spectroscopy of the Unitary Fermi gas.
Okay, great. So thank you very much. So firstly, I'd just like to start by thanking the organizers of the conference. So not just for the opportunity to talk today and to tell you about some of the work we've been doing at MIT in Boston, in the US, but also for putting this conference together and for organizing it so well. So thank you very much. So my name is Richard Fletcher, and I'm a researcher at MIT. And so the title of my talk today is Acoustic Spectroscopy of the Unitary Fermi gas. And this is some work that's still very much work in progress and very much ongoing. And so our understanding is really still evolving. So I'm looking forward to some nice discussions. And in fact, some of the results I'll be showing were really taken in the last few days or so. So there's been some healthy exchange of emails with the grad students back in the lab. So I'd just like to begin by introducing the group. So we're all under the umbrella of Professor Martin Zwirlein, who's this guy down here. And so we're an experimental cold atom group. And I'd just like to single out the people involved in this project. And so this work on sound in the unitary Fermi gas was really spearheaded by Julian Struck, who was a postdoc in the group, and he left about 1 month ago to go and start a position at ENS in Paris. And since he left, the mantle has really been picked up by Parth Patel, one of the graduate students. And then just at the end, I'll try to mention some of the other projects we have going on in the lab. And these are really being carried by Bishrut Mukherjee and Zenji Yan, who are two of the other grad students in the lab. So we're really blessed to have some very, very good students with us. And so I just wanted to acknowledge their contribution at the start. Okay, so just first to offer some outline of what I'll be speaking about, I'll begin by, and I realize this is a very sort of general audience with a lot of different interests, so I hope I don't insult anyone's intelligence by starting with quite a general introduction to the systems that we're working with, which are very cold systems of fermionic atoms. I'll then talk about the experiments we've been doing where we're injecting sound into this gas and trying to learn something about it. And then the first thing you might want to study when you look at sound would be something like the dispersion relation. And we're measuring the speed of sound and seeing how that varies with temperature, for example. And then I'll talk about some of the experiments we're doing looking at the damping of this sound. So how does this sound attenuate as it propagates through this Fermi gas? And so far we can identify like two distinct regimes in our system, namely the hydrodynamic regime, when the phonons in your gas really collide with each other very frequently, and the collisionless regime, where it's better to think of these well-defined quasi-particles zipping around inside your cold gas. And then finally, I'll offer some outlook on this project, and then finish up with, I'd like to just mention some of the other projects we have ongoing on this machine, and also to mention a new experiment which we're setting up in the group at the moment. Okay, so the systems that we work with are very, very cold gases of fermionic atoms. And so we work with lithium-6, which is a fermionic isotope of lithium. And so for most cold atom experiments in the world, these atoms are going to be confined in a harmonic trap. And that's simply because harmonic potential is the easiest sort of trapping minimum you can make, whether you're working with magnetic fields or optical fields or so on. And that's been a very successful platform. But one thing it does make a little bit more difficult is obviously proving homogeneous properties of a system. So for example, if you want to look at correlation functions or if you want to look at critical phenomena, then what you'd really like would be to have a uniform system where the density is homogeneous throughout space. And so what we have at MIT was actually the first 3D uniform trap for fermions in the world. And the way we make this is that we take a hollow tube laser beam. Okay, so this is a laser which is dark at the center and just has this bright edge. And we propagate it along some direction. And then we intersect that with these two very sharp wall beams. And that confines our atoms to a sort of soda can-shaped region in space. And so this is here just an illustration of our atoms trapped in our lasers, whereas these two images here are real absorption images of our gas. So these are projections of the density of the gas onto a particular plane, either taken axially along the cloud or radially. And so we're working with fermionic atoms, and in fact we trap two different internal states. And so we put our lithium-6 atoms into two different spin states, and we have a roughly equal mixture of the two, which you can think of as these distinguishable red balls and blue balls. And the reason that we do that is that to a very good approximation, our atoms interact with each other via a contact interaction. And so if you had identical fermions, if everyone was in the same internal state, then just Pauli exclusion would stop these two fermions ever being on top of each other. And so what you'd end up with would really be a non-interacting Fermi gas. So if we want to introduce interactions, we need to work with two different spin states. And so the interactions between these atoms are described well by a contact interaction, and that's simply because the various length scales in the gas, such as the thermal wavelength, or the interparticle spacing, are all much bigger than the range of the potential. And one of the nice things, yes, of course. So the interactions between the atoms really does arise from the van der Waals force. But the van der Waals attraction has a certain length scale associated with it, and that's much smaller than both the scattering, sort of effective scattering length, which would describe that interaction, and also the distance between the particles, and also with the thermal wavelength of the gas. So from the point of view of the atoms, they just don't have the high momentum components in their wave function, which you'd need to sort of explore the short distance behavior of the potential. So it's really, I mean, one of the kind of big advantages of the system is that you can ignore the sort of perhaps slightly more complicated real interaction potential and just replace everything with a contact potential. And that makes, theoretically, things are more straightforward, and it's also still a good physical approximation to make. And so one of the big advantages in these cold gases is that we have the ability to actually tune A, which is the S-wave scattering length, to any value that we like. So we can make these atoms either non-interacting, we can make them weakly repulsive, weakly attractive, and we can actually dial up A to be as large as we like, so we can make a really strongly interacting gas. And what this has let people do is study in these very controllable systems really strongly interacting many-body quantum systems. And what I mean by many-body, just to take one example, if we consider the case of a positive scattering length, so this is then a repulsive contact interaction, and if I have two particles interacting via that, this supports a two-body bound state, and that's going to have some extent roughly given by the scattering length. And so if we can dial our scattering length to be much larger than the interparticle spacing, then the size of these molecules starts to become larger than the distance between particles, and so the pairing of fermions really becomes a many-body process. You can't just think about individual pairs of particles forming their dimers. The density of the gas. Okay, and so over the last couple of decades or so, this has been a very, very rich system to study. And one of the sort of most famous examples of physics to come out has been the so-called BEC-BCS crossover. And so what I'm showing here is a phase diagram, which is some parts of which are still very much under debate, but just to give a general idea of the kind of phases you expect in this system as a function of temperature on the y-axis, and something like 1 over A, or really a comparison of the scattering length to the interparticle spacing along the x-axis. And so out on the right-hand side of the axis here, this corresponds to a positive scattering length. So here, this potential supports the two-body bound state. So the ground state of the system is such that the two fermions of opposite spin will bind together to form a real space molecule. These then behave as composite bosons and can undergo Bose-Einstein condensation. And then conversely, on the left-hand side, this region corresponds to a negative scattering length. So here there's some attraction between the particles. And just like in, say, an S-wave superconductor in a metal where spin-up and spin-down electrons can bind together and form Cooper pairs, these atoms can form Cooper pairs. So this is pairing in momentum space, and we get a BCS superfluid of these fermion pairs. And in the center, there's this very interesting regime. And this is known as the unitary Fermi gas. So here the scattering length, which is the only number in the system which characterizes the strength of interactions, has diverged. Okay, but our system still has to be a well-behaved thing, and so you can't have infinities appearing everywhere in your description. And so somehow the scattering length has to disappear from any description of the gas. So you're left with a very strongly interacting quantum gas, but in some sense the physics becomes universal. And what I mean by universal is to say that because the scattering length has disappeared, we're only left with two length scales in the system, which is the interparticle separation, so density to the power of -1/3, and the thermal wavelength. And commensurately, you're also left with two energy scales, the Fermi energy and also the thermal energy. And so lots of physics can only depend on ratios of these energies. And just to give an example of the kind of universality that pops out, if we think about the speed of sound in this sample at 0 temperature, well, we know that for a non-interacting Fermi gas, you can calculate fairly straightforwardly that the speed of sound is roughly set by the Fermi velocity with some prefactor, which ends up being 1/√3. Now, when we go to unitarity, you might at first think this is a complicated, it's a many-body quantum system. Surely the expression is really going to look very different. But if we're sitting at 0 temperature, the only length scale in the system is the interparticle spacing. And the only velocity I can construct in the interparticle spacing is the Fermi velocity. So in fact, when we go to unitarity, the only thing that can change is some dimensionless prefactor. And so for the unitary Fermi gas, all that changes is we pick up this dimensionless prefactor, psi, which is known as the Birch parameter. And the reason people talk about these systems being universal is that this Birch parameter should be the same number whether you're working with lithium atoms or potassium atoms, or whether you're looking at, say, neutrons in the crust of a neutron star. So any Fermi gas where the scattering length is much larger than the interparticle separation, this number should be the same. It ends up being about 0.37. Okay, so one of the big motivations for the whole field of ultracold atoms is that quantum many-body systems are interesting. They display interesting physics, and they really appear over all different length scales in the universe. And so trying to understand how these things work is an important thing. And so this is made pretty difficult, which is something that I'm sure I don't need to emphasize with this audience, and that's for a couple of reasons. And the first is that it was perhaps nicely summarized by Phil Anderson back in the 70s in this essay entitled More is Different. And the point Anderson was making is that just because you understand how 1 or 2 quantum particles will behave doesn't mean you understand how 1 billion will. And so you can get this new collective behavior emerging somehow out of the sort of complicated microscopic collective behavior of these many constituents. And then just to make things a little bit more tricky, the fact that the Hilbert space in which your state vector, which describes the state of one of these many-body systems, grows exponentially with the number of particles. And that means that computationally, I'm sure any theorists in the room know, these can also be very challenging systems to understand. And so these two facts just conspire to mean that these systems are both complicated and interesting, but also very challenging theoretically. And so when you're thinking about collective phenomena, one of the paradigmatic examples is really sound. And so sound is a new phenomenon that emerges once you have the interplay of many, many constituents. And so if I was a scientist living on a planet on which there was only one nitrogen molecule, so apart from the obvious respiratory challenges you might face, you could study everything you wanted to about this molecule, and you could learn all about its rotational properties or its energy levels, but nothing you studied about this nitrogen molecule would tell you about sound. And so it's only once you have this room full of 10 to the 24, 10 to the 25 nitrogen molecules does this new phenomenon emerge where these density waves can propagate through the gas with some kind of well-defined properties. And so sound has therefore been something that people have been very interested in studying in these cold quantum gases. And so just as an example, I've put up this experiment from Innsbruck. And so I do apologize. I mean, a lot of groups and people have worked on sound in cold gases. So I'm sorry if I've missed off people's experiments or people's favorite experiments. But I think this is just a nice illustration of the kind of phenomena you can see in these systems. And so what they did in this experiment was they took a cold Fermi gas, which is shown by this purple oval here, and it has a superfluid core, which is this darker purple at the center. Okay, and this red beam here is just their trapping beam, which holds their cloud. And then they send in this green laser beam, which lets them modulate the potential at some point in space. And so by applying different excitation protocols with this green beam, they could excite various sound modes. And so they were able to observe both first sound, which is, you can see in this plot here, where this is distance along the cloud, and this plot here is time. And you can see these two density perturbations just propagating outwards through the gas. And then by modifying their excitation protocol, they were also able to excite second sound. So this is if you locally can heat the gas. What they see, again, is two little density perturbations propagating outwards. But this time, the speed is really changing as it moves out through the gas. And also the reason you can tell this is second sound is that this modulation can never cross the normal to superfluid transition. So this white vertical dotted line is just showing the superfluid to normal transition in the gas. And this density perturbation, the speed just slows and slows and eventually vanishes once it reaches the edge. And the reason that you might think initially, how are they observing second sound, and that's generally thought of as being purely a density wave. The point is that in these gases, a change in temperature also results in a change in density. So there's some coupling between the two, which means if you modulate temperature, this temperature wave also corresponds to a density wave, which lets them observe it. So this is in this experiment, they're sending in a laser, and the laser really just exerts a force on the atoms. If you send in a laser beam that's far detuned from any atomic resonance, this imposes a conservative potential on the atoms, which is proportional to the intensity of the laser light. And so you can think of the laser beam as simply being it's a potential, and you can control it, both its shape and its time dependence. But it's purely conservative thing. Okay, and so this is a very nice experiment, but one thing that can make the interpretation slightly tricky is the fact they're working with an inhomogeneous sample. So all of the properties they're probing are going to be averaged across this, the various densities in the system. And so what you'd really like to do would be to do something like this experiment, but this time in a homogeneous system. And so that's what we set out to do in our experiment. So we're working now with this homogeneous Fermi gas. And so what we'd really like to do is to take our homogeneous gas, and just like if we had a tank of water, simply modulate one of the walls, inject sound into the system, and then try to learn something about it. And so maybe if you inject the sound, you might be able to look at the frequency of the sound you inject, its wavelength, perhaps its damping with space, and try and learn some interesting physics. And so this is a little video of some people doing a similar experiment with water, which I think looks like a really, really fun lab to be involved with. And so we wanted to do something just like this top picture, which is with a large tank of large swimming pool, but instead using a quantum gas of a few thousand atoms down at a few nanokelvin in temperature. And so this is, again, this is our quantum gas, so how are we going to inject our sound? Well, in principle, you could move the position of these walls, and that's possible. Experimentally, it's a little bit of a pain to do. Luckily, we're experimentalists, and we never build our experiments perfectly, so we can simply make use of our experimental imperfections, which is that we can never really make perfectly sharp walls. There's always some diffraction limit for how sharp features you can construct are. So our walls always have some finite slope, and all we do is simply modulate the power in one of our end cap beams, and the fact there's a finite slope to the potential, this translates into a time-dependent force on the edge of the cloud. And so this picture in the top right shows our trapped atoms without any excitation. And then after driving our wall for some time, this is what you see. And at first, perhaps you stare at your computer screen, you're a little bit disappointed. But if you simply subtract off this first image, which is sort of the unperturbed system, and choose a more forgiving color scale, then what you see are these nice ripples and this nice density modulation propagating through the gas. So here, red corresponds to an enhanced density, and blue corresponds to a reduced density. And if we just integrate out the boring direction along this direction and plot just as a 1D plot, so this is vertical position in the cloud, and this is the fractional change in density, then what you indeed see is this nice density modulation propagating through the gas, and also clearly displaying some kind of damping. And so during the talk, what I'd like to mention are two protocols which we've tried out for injecting sound. And so the first is what I'd call free space propagation. And this is where you simply modulate one of your end caps, you excite some wave, and you just don't give the system time to realize there's another boundary condition. So in some sense here, you're probing sort of free space propagation in the system. And just thinking momentarily about the sort of Fourier limits this puts on things, this obviously limits you to working with timescales less than something like the length of the box divided by the speed of sound. And so conversely, we're always going to have some kind of broadening in frequency space given by the speed of sound over the length of the box. And so this protocol is only really suited to relatively high frequencies, which would correspond to sort of very high modes inside this box, where the system doesn't really realize there are boundary conditions on the problem. And then if you want to look at low frequency behavior, now the system has to recognize that there are two walls. And so instead what you can do is just drive both of your walls, give the system time for waves to go back and forth, just like the way you drive an optical cavity, and look at the resonant modes in the system. And so I'll first just mention this free space propagation case. And so what we do is we take our gas, we modulate the power in one of our end caps, you get some density modulation, you can then plot that as a function of distance, and you can extract for a given driving frequency what's the wavelength of the sound that you excite. And perhaps no big surprise, what you find when you plot this data is a nice linear relationship. And this is just what you'd expect from a kind of phononic dispersion relation. And so from the slope of this dispersion relation, one can simply extract the speed of sound, which in our gas, for this particular Fermi energy, corresponds to something like 1.5 centimeters per second, which is sort of a pleasingly macroscopic number to appear in this very, very cold gas of just a few thousand atoms. I guess this is the phase velocity. So this is simply, we excite at some frequency, and then you just look at what is the K which appears in your system. So it's really just at a given omega, what's the K? Yeah. So, well, I guess in this, for a linear dispersion relation, it's group velocity or phase velocity. I mean, this is simply the gradient of this line. Yeah. I agree. If there was some curvature on this, then you'd have to start distinguishing the two. But we've never been able to measure anything other than a linear dispersion relation. Okay, so one of the first things that we set out to do once we'd done this was to see how the speed of sound varies with temperature. And that was for a couple of reasons, one sort of scientific and one slightly more emotional. So scientifically, studying how something changes with temperature is often an interesting thing to do, and it can tell you something about the underlying physics. But perhaps more emotionally, it just seemed like a fun exercise. And the reason for that, which I'll just outline on this slide, and there are only 2 slides in this talk which have sort of any reasonable amount of maths on, and this is one of them. So it's titled, E equals mc squared, question mark. And if we just think about what the speed of sound in this gas should be, well, we know that generally in some hydrodynamic medium, the speed of sound is really given by the adiabatic derivative of the pressure with respect to the density. And so the pressure in turn is given by the adiabatic derivative of the energy, the internal energy with respect to the volume. And this is where the fact we're working with a unitary Fermi gas makes things a lot more simple. And so the energy of the gas has to, just because of the few length scales you have to work with, needs to simply be given by the energy of a zero temperature non-interacting Fermi gas with some dimensionless prefactor which will contain all of the effect of interactions, which in this case has gone up to infinity, and temperature, which will be some ratio of the temperature to the Fermi temperature of the system. And that means that if we're taking this derivative at constant entropy, this dimensionless prefactor, which will be it might be some complicated function of T over Tf, has to be kept constant. Okay, if we're keeping entropy constant, that dimensionless prefactor needs to be constant. And what that means is that this derivative ends up being very easy to do. And so what you find is the pressure is just given by some possibly unknown, maybe complicated prefactor, but it's dimensionless and it's a function of entropy, and then simply the energy of a zero temperature ideal Fermi gas. And so these derivatives all become very straightforward to do. And what you end up finding is in fact that E equals 0.9 mc squared. So a little bit of a deviation from what Einstein said. We plan to get T-shirts printed immediately with this on them. But we thought this was a fun prediction, and so we set out to test it. And so this is where we ran into a little puzzle that we thought about for quite a long time, and that's how to measure the energy of this trapped gas. And so one of the disadvantages of working with a box of gas is that whatever you do to this thing, whether you increase its energy or you increase the temperature or change the interaction strength, the box of gas still looks like a box of gas. And so how do you extract the energy from it? And so this is another instance of where we can make use of an experimental imperfection. And so, little tip for any experimentalists out there, you never make your experiments too perfect. These things can sometimes come in useful. And so we can never quite get rid of any background curvature in our potential. And so there's always some residual harmonic confinement to our gas. And so all we do is we simply switch off our sharp and confining walls. This will then be followed by some complicated, very non-equilibrium dynamics. The gas is going to flood out into this harmonic trap. But after some time, there'll be some redistribution of energy, and the gas will settle back down to some steady state. And importantly, even though we don't really understand what the dynamics of how this box changes into this harmonically trapped gas, we know that we haven't added or removed any energy. Okay, all the potentials here are conservative, and all we've done is remove these 2 very sharp walls. And so now that we have our gas living in a harmonic trap, it's much easier to extract the energy. And in fact, this is a nice case of where you can employ the virial theorem. And so you know that the total internal energy of this gas can simply be extracted from the mean potential energy, which you can just read off by knowing your harmonic trap and by measuring what your density distribution in space is. And so with very, very little fanfare, actually, this is what we end up seeing. So this is a plot of mc squared on the y-axis against the per particle energy of our gas. And so what you see is a fairly nice linear relationship. And when we fit this thing with a line, what we end up finding is that E is equal to about 0.83 mc squared. And so we end up about 1 sigma away from this prediction of 0.9, which we were just quite pleased to see. And I'll just add that the superfluid to normal transition occurs around here. I mean, actually, certainly in this plot, very little dramatic happens. And so first sound exists both above and below the transition. So we don't really see any kink or any sudden change here, which is sort of what you expect from what we've just discussed. Okay, so that is what I wanted to say about free space propagation. And so now moving on to these resonant modes. Okay, so the idea here is that we drive the two end caps. We drive for some long amount of time, and long meaning that a sound wave has plenty of time to bounce backwards and forwards in our cavity. And then we just measure what the amplitude response of the system is. And so what you're seeing on the right-hand side here, this is a plot of the in situ density perturbation as we scan the frequency of our drive. And so I'll just wait for the video to start again. But the points I want people to take away from this are firstly that as we scan the frequency, you gradually see higher order modes appearing, which is good. That's sort of what you expect. But secondly, their contrast clearly changes. So that's a lower order mode. And as we go up to the next one, still pretty good contrast. Okay, and then we're between modes, nothing much happens. Then we hit a new resonant mode. Contrast is maybe falling now. Okay, and by this point, it's certainly lower. So as we go up, we see these higher order modes, and their contrast is clearly falling. Okay, so the experiment looks like this. We can drive our end caps at a variable frequency. We then extract what the density perturbation looks like. We integrate along the boring direction, which gives us some vertical slice. And then we stick all of these together. And so what this plot is showing, this is the amplitude response as a function of frequency along the x-axis and of position in the box along the y-axis. So we call one of these pictures a sonogram, and it's sort of an acoustic picture of the sound behavior inside our gas. And so when you're working with a homogeneous system, and generally position is not such a useful number to be thinking about. So the first thing that we then do is just do a Fourier transform, a one-dimensional Fourier transform of the density distribution in the vertical direction. And so then what you get is something like this picture on the bottom. So this is now k, so this is wave number on the y-axis, and this is now frequency, still frequency rather, on the x-axis. And then the color scale corresponds to the amplitude of the Fourier transform at that k and at that frequency. And so just like when we're doing the free space propagation, you expect to see some kind of linear dispersion relation, and that's exactly what we see by these bright points in the Fourier transform here, which lie along some straight line in omega k space. But you can notice a couple of things from this picture. The first, which I'll come back to just after this section, is that the width of these modes in frequency space is clearly increasing. Okay, so the amplitude response, the magnitude of the amplitude response is falling, and the width is increasing. And this points to some kind of increased damping in the system. And the second thing is that probably the numbers on these axes may be too small to read properly, which I apologize for. But we're actually only seeing every other mode here. So this is actually the second mode. There's n equals 2, n equals 4, n equals 6, and so on. And the reason for that is very simply that we're shaking symmetrically. So we're modulating both of our end caps in phase symmetrically, which means you can never have a mode which has some non-zero center of mass motion. And so we can remove this constraint simply by modulating only one of our end cap walls, and then, sure enough, we see the number of modes that we observe double. So this is modulating both end caps. This is modulating only one end cap, and this time you see every mode. Okay, and so once we saw this and saw how the width and frequency space of these modes was changing as we drove these resonant modes at higher frequencies, this prompted us to start thinking about damping. And this is somewhere where working with a homogeneous system is really a big advantage, because we're not having to average anything over different densities where the damping properties might be different. And so quite generally, what we mean by damping is that the sound mode we inject is somehow coupled to some other modes in the system, and so you get a loss of energy from the initial sound mode you've injected into some other degrees of freedom. And we're very much new to this, and so we're learning a lot of new stuff all the time. And certainly if you go back and read the literature on these sound propagation experiments done in liquid helium, there are really a lot of different regimes one can consider in terms of what the dominant processes which bleed energy out of your sound mode into some excitation of the gas are. But in our system so far, we've just identified two distinct regimes. The first of those is hydrodynamic, and the second is the collisionless regime. And so hydrodynamic, what we mean by this is the frequency of our phonon mode multiplied by the sort of typical relaxation time of a quasiparticle is much less than 1. And the idea here is that a phonon will really scatter many times during one of its oscillations. And so here it's best to think about the propagation of sound in some kind of hydrodynamic picture, okay, where there's this gas of excitation is somehow a hydrodynamic fluid, which is scattering rapidly enough to always be trying to thermalize itself. And so in the opposite limit, where the frequency of a phonon is much larger, and so this means the phonon collides few times in one oscillation. Here it's much better to think about these phonons as being somehow well-defined quasi-particles, which are zipping around inside your superfluid. They're well-defined, they wiggle many times before they undergo a scattering event, and this time the question becomes, what are the processes by which perhaps two phonons can merge into a new one, or perhaps a single phonon can split into new phonons, and so on. And so thinking first about how we might identify this hydrodynamic regime, well, whenever we're thinking about hydrodynamics, you always start by considering a general element of fluid, which is always drawn in this kind of peanut-type shape. And then we can write down a couple of equations. So we can think about the continuity equation, which is some kind of a differential equation in terms of the density of the gas, rho, and Jz, which is just the flux. So this is some kind of product of density times velocity. Everything's just one-dimensional here. And we can also think about the momentum equation. So this is sort of comes from considering the forces on this little element. And in the momentum equation, rather than simply writing down some kind of Euler equation where you ignore any kind of viscosity and so on, you can also include this extra term. And this can arise, for example, from viscosity, which applies some kind of penalty for ever creating a velocity gradient within your system, or also maybe from diffusion, okay, where flux or momentum flux can actually diffuse from one part of the gas to the other. And so everything's linearized here, and so these equations are pretty straightforward to solve. And just by substituting in some traveling wave equation, what you find is a dispersion relation where the first part just looks like your familiar linear phononic dispersion, so just omega equals ck. But then we have this extra term, and this corresponds to damping. And specifically, this term would correspond to a damping rate, which should be proportional to frequency squared. Okay, so this is sort of a hydrodynamic prediction for what this damping should look like. And so the intuition there is that at higher frequency, not only are my velocities higher, but also the gradients of my velocities are higher. And so that's sort of where you pick up these two powers of frequency. So in our system, we think this viscosity is probably the dominant term here. And so the contribution of viscosity to this sort of diffusion type or diffusivity type coefficient here ends up being something like kinematic viscosity. Okay, and this is something that we were very pleased to see. And the reason for that is that the sort of ethos of hydrodynamics is that you say that there's lots of complicated microscopic physics going on in my system, and in general that's going to be really hard to understand. But you say that if some kind of thermodynamic equilibrium is established, then I can ignore this microscopic physics and instead talk about some kind of coarse-grained description, where I think about fields such as density field or a temperature field or a velocity field and so on. But unfortunately, this complicated microscopics, you can never quite get rid of it entirely. Instead, what you do is you package together that unknown physics into some phenomenological parameter, so for example, the viscosity. So whereas this viscosity can appear in a well-defined way within your equations, actually calculating it can be a difficult thing to do. And so the idea that we could actually measure viscosity from the damping of our sound was something that we were quite pleased to find. And this is something that's been known in the liquid helium community for a long time, but it was new to us, and so we were excited to find it. Okay, so this is the experiment that we do, and we work with a reasonably hot gas. So this is T over the Fermi energy of roughly 0.3. That doesn't sound very hot. Just to give you an idea, the superfluid transition is at about 0.17, so we're at something like twice the critical temperature. We take one of these sonograms, we do the Fourier transform, and then we just look at the width of the various modes as we go up through frequency. And so this plot here is showing, for each mode of the box, shown by a different color, this is just a cut through this Fourier transform along a line of constant wave number. And so you can see that as we move from the lowest mode to consecutively higher modes, this width is gradually increasing. So what we can do is we can fit these with some appropriate function, extract their width, and what we indeed see is a nice quadratic relationship, where the damping of these modes indeed goes quadratically with the frequency. And so, having established this quadratic dependence, the next thing you can do is to try to extract the viscosity. Now, just on dimensional grounds, you know that this kinematic viscosity, which is this ratio of the shear viscosity of the gas to the density, has to be given by some dimensionless prefactor multiplied by h bar and m. This is just a dimensional argument. And so, by just fitting a line to our data, what we find is that for this particular temperature, we find a prefactor of about 2. And this is quite nice in that this really tells us that we're starting to hit sort of quantum regime of viscosity. where this sort of scale of h bar and m really sets the shear viscosity of the gas. And just to give you a sort of point of reference, the kinematic viscosity for water is something like 500 to 1,000 h bar and m instead. So I think that would be a very interesting thing also to look at. I mean, I guess you're referring to these ideas that there should be some universal lower bound to that ratio. Yeah, so that's very much something that we'd like to start to think about as well. I guess you need a good way to then measure entropy density. And so, I mean, the way that for example, the Duke group with John Thomas have done that in the past is that you do just some adiabatic transformation of your complicated gas to something a bit simpler, extract the density, the entropy from that new gas, and then infer what the entropy must have been in the old gas. For us, we actually know the equation of state for the unitary Fermi gas. This was measured at MIT a few years ago. So we could probably just extract our entropy directly. And so absolutely. So looking at that ratio of shear viscosity to entropy density it's on our to-do list. But yeah. Okay. So that's the hydrodynamic regime, and then moving now instead to the collisionless regime. So now the idea is that the scattering of these phonons is much more rare. So there's not some kind of thermodynamic equilibrium between the phonons. We can't think of them as being some hydrodynamic fluid of excitations. Instead, we have to think about these quasi-particles and what might couple them to each other. And so in our gas, I'll come back a little bit to the types of processes that might happen a few slides later. But in our gas, we think there are really two possibilities that could arise. And the first of these is Landau damping. The idea of Landau damping is that a phonon from the mode you've injected, which is this blue arrow, can scatter or can merge with a thermal phonon. So that's just sitting in your finite temperature. There's some blackbody spectrum of thermal phonons. Two of these guys can merge together to give you a third phonon. And this coupling will be provided just by any higher order terms in your Hamiltonian. So your Hamiltonian is never perfectly diagonal in sort of phonon creation and annihilation operators. There are always, say, terms involving 3 creation and annihilation operators, or 4, or so on. And all of those terms can give you coupling between these phonon modes. And the other possibility would be Belyaev damping, where one of your phonon modes that you've injected can just split into 2 new modes. And this would be a leaching or bleeding of energy from your sound into lower frequencies. Okay, and so when thinking about this, we've really gained a lot of insight from this theory paper, which only came out a couple of months ago, which was sort of very, very good timing for us. And this is from Yvonne Castan and Alice Sinatra in Paris. And what they do is actually calculate exactly the damping rate of a phonon in a unitary Fermi gas due to these 2 processes. And so this plot is just showing the damping for a particular K, they call it Q, this is just the wave number of the phonon, against some kind of ratio of Q, of the Q to temperature. Okay, this is just some dimensionless number which ends up being a convenient parameterization for them. And what they find is that depending on the temperature you're at, this Landau process and this Belyaev process can have different weights of contribution. And so in our experiment, unfortunately, we're really restricted to working down here in the scale. It's just very, very difficult to get cold enough or to get to high enough Q to move up towards this right-hand side. So in this regime, this corresponds to relatively high temperatures, and that means that Landau damping should really be the dominant process. So that's given by this curve here, which down in this regime is almost everything is almost entirely Landau damping. And this is kind of intuitive that this should dominate at high temperatures, simply that if your gas is hotter, there are more thermal phonons zipping around. And so this process where you're going to scatter off an existing thermal phonon should be the dominant process. And so the prediction that's made in this paper is that the damping rates in this case should actually go linearly with frequency, and there should be some temperature scaling, which ends up being T to the 4, and this just is due to the fact that the hotter you are, the more thermal phonons are around, and so the higher the damping rate should be. And so now we work with a gas which is below the superfluid transition temperature, so it's quite a lot colder, so the T on TF of about 0.13. And this is what we get if we measure the damping of our phonon mode as a function of frequency. And so as opposed to the hydrodynamic regime earlier, we now see this linear dependence. And what was quite nice here is that the two colors on this plot correspond to extracting the damping in 2 different ways. And so the blue points correspond to extracting this damping rate from, again, looking at our sonogram. So we're looking at the width of the amplitude response in frequency space. And the red points come from looking at higher frequencies of simply injecting some sound and just looking at what the attenuation of this sound is. And so from how it attenuates with distance, knowing the speed of sound, you can then extract some damping rate. And so these two data sets really agree pretty well with each other, which gives us some quite good confidence that we know what we're observing. And so once we'd seen that these two approaches also agreed, one can then think about these modes in the system. Just as a very simple analogy is just a driven damped oscillator, so some kind of mass on a spring in some oil. And this is a problem that everyone studies in undergraduate physics. And you know that from studying this type of system, the damping coefficient sets various widths. And so it's going to set the frequency width of the amplitude response, and this is something that we've measured. It'll also set the time scale of a ring down. So if you inject some excitation, what's the time scale or the distance scale over which this wave will be damped? And it should also set the frequency width of any energy deposition. And so we set out, just wondered if we could see this type of behavior. And so all we did is that we shook our box at a particular frequency for some time. We know how to measure energy of the system just by releasing into a harmonic trap. And so this is what you see for a reasonably high temperature gas. This is a plot of the energy in the gas as a function of the shaking frequency. And you see these sharp peaks at the various modes of the box, but these start to get washed out pretty quickly. And that's just because the width of these peaks is really growing quadratically with frequency, and so it just grows fast enough that these start to become not very well defined. So conversely, if we now look at a much colder gas, the damping should be much lower. It's now scaling just linearly with frequency, and so now these modes show up a lot more cleanly. Okay, so just to first offer some conclusion of this work before I'd like to mention some of the other projects we have going in the group. So we've demonstrated acoustic propagation in a unitary Fermi gas and started to study the various damping mechanisms in this system. We found indeed the speed of sound is set by the internal energy and slightly modified Einstein's result. So in fact, E is 0.9 mc squared. And then in the hydrodynamic regime, which we identify by the quadratic scaling of damping with frequency, we can make some first measurements of viscosity of the system. And then in the collisionless regime, we instead find a linear dependence, which is what you expect, so the characteristic scaling which should arise from Landau damping. And so some outlook of what we'd like to do next, so what we're really currently working on, and by currently I mean it's happening today. So the first thing we want to look at is try and learn something more about the various nonlinear effects in the system. And what I mean by nonlinear effects, this is anything which is taking phonons and coupling, say, two phonons into new frequencies and so on. And so an example of a nonlinear effect would be second harmonic generation, which we actually do see some evidence of. So to show what I mean by that, this is something we're still trying to get a more quantitative handle. But if we look at a propagating wave in our gas, what we find is that a single sine wave, it does not a bad job, but it doesn't do a really perfect job of fitting our density profile, which is the density profile is this blue line here. And instead, if we fit by including the second harmonic, so allow some admixture of a sine wave at twice the frequency, we get much better agreement. So this is so far fairly qualitative evidence for second harmonic generation, but it's something that we'd like to pin down a bit more in the next few weeks or few months or so. And the other thing one can think about doing is looking at some kind of what we call stimulated Belayev damping. Okay, and the idea there is to say inject some sound, for example, some frequency omega, and then also inject some sound at the frequency of half that. And what we wondered if we could see is if you already have some population of the lower frequency mode, can that somehow stimulate the higher frequency to actually undergo Belayev damping, so for phonons to split into two lower frequency phonons and sort of populate this lower frequency mode, and whether you can see some kind of bosonic stimulation of these phonons. We'd also like to try and push to higher frequencies. So far, all of the frequencies which we're looking at are quite a lot below the pairing gap, and that means that these are purely bosonic excitations. So whereas once your frequency starts to become comparable to the pairing gap in the system, you should start to get some coupling of this density modulation to actually breaking of pairs, and so creation of fermionic quasi-particles inside the system. This is quite difficult because, as you've already seen, the damping of these modes grows as you go to higher frequencies. So what we're struggling with at the moment is just getting a sort of large enough density perturbation in the first place at the frequency which you care about. But one could imagine, for example, going onto the BCS side, the pairing gap there should come down, and perhaps that should move the pairing gap into a regime which we can actually access by injecting phonons. And then thirdly, something that from speaking to theorists, people are quite interested in is looking at the effect of the curvature of the dispersion relation on the various decay mechanisms. And what I mean by that is that if one thinks, for example, about either a linear or a slightly convex dispersion relation, So this is just sort of omega. I've written energy, but it's really just omega against k of your sound. If there's a slight convexity, then the dominant process should be either Landau damping or Belyaev damping, which is what I've discussed in our case. And that's where either one phonon can split into two, or two phonons can merge into one. If instead your dispersion relation is concave, it takes you about a page of maths to show that these processes are not allowed. So there's no way you can conserve energy and momentum by taking a single phonon and splitting it into two, or vice versa, if your dispersion relation is concave. And so in this case, the dominant damping mechanism in the collisionless regime should instead be so-called Landau-Kalatnikov damping, which is where two phonons can merge with each other and produce phonons of two new frequencies. And this should display sort of new scalings with frequency and so on. And so what's quite nice is that in the Fermi gas, as you scan across the BC-BCS crossover, the dispersion of the curvature of this dispersion relation is predicted to change. And so actually the nature of the damping mechanisms in the collisionless regime should be different depending on where you're sitting. So I'd just like to finish in the last couple of minutes just by mentioning some of the other projects that we have going in the group. So on this machine with a homogeneous Fermi gas, something we're trying to do is to take advantage of the fact that there's no averaging over homogeneous densities. And so that lets us really probe the superfluid transition in all sorts of different spaces. And so one experiment which we've tried is simply just applying a linear potential gradient to our box and just looking at how the density of the gas changes. And this is really a kind of textbook measurement of the compressibility of the gas. It's really measuring what's the change in density for a given change in chemical potential. And so what we see as we measure the compressibility, as we scan the energy of the gas, as you approach the superfluid transition, which is given by this line here, then you see this sharp peak in the compressibility, which gradually starts to fall downwards. And so this is the kind of lambda-type transition in compressibility which you expect as you cross the superfluid transition. We're also looking at the condensed fraction. This is something there's been a lot of, sort of theoretical discussion of in the last, I guess, really since the advent of superfluidity in Fermi systems, in cold Fermi systems. And that's just looking at what's the population of zero momentum pairs in your system. So it's slightly involved how you do this, but what you can measure is the momentum distribution of pairs. Okay, and what you find is that if you're in the superfluid regime, if you measure this momentum distribution, what you find is a broad thermal background and then this sharp peak at zero momentum. And this corresponds to a big population of pairs sitting at zero momentum. But exactly what this population should be is something that is still very much under debate and really depends on what theoretical approach you take. And so we can make quite a nice measurement of this quantity. And something that's quite interesting that we want to look into further is that if you look above the superfluid transition, we do actually see some kind of bosonic enhancement of zero momentum pairs. So this is the momentum distribution of our pairs above the superfluid transition. Whereas the wings are well fitted by a Gaussian, when you go towards the center, we actually get a much better fit just by fitting with some kind of polylog. And this is the fit function you'd use for bosons as you approach the critical points. So there seems to be some kind of bosonic enhancement of zero momentum pairs, even when you haven't reached the superfluid yet. So whether this is a signature of some kind of pseudo-gap regime or some kind of pairing already above the transition, that's something which we're still looking into. And this is a plot, by the way, this is the condensate fraction against energy, which is slightly easier for us to measure than temperature, but we could also plot it as a temperature axis. And then something else that we're measuring, or trying to measure, is the so-called contact. And so the contact is something that's emerged in the last few years or so, and it's really a measure of the strength of short-range correlations in a system. And so there are various ways you can measure this, and one of the reasons that the contact is quite a powerful quantity to think about is that once you know contact for a particular system, that will then show up in all sorts of different observables, such as the momentum distribution, or how the energy changes with scattering length, or the RF line shape, and so on. And so what we do is we just send in a radio frequency pulse that transfers some of our atoms to a new spin state, and by looking at your transferred fraction, that gives you some kind of measure of the overlap between your initial interacting wave function with the final wave function of the atoms you transfer into. And then just really, really finally, this is a new experiment which we're currently building in the group. And this is really being specifically designed to offer quite a powerful and quite a versatile platform to explore the Fermi gas in 2 dimensions. And the basic setup will involve a glass cell, which gives us very nice optical access, certainly a lot more than in our current machine, and a very high resolution objective sitting right against the glass. And the idea here is to really bring in 2 of the sort of big technological advances of the last 5 to 10 years or so in the field. And the first of those is the ability to resolve single atoms in a system. So this is an image taken from one of the other groups who work just next door to us, where every dot in this picture is a single atom. Okay? And so this ability to take a many-body quantum system and actually see what every single atom is doing is quite a powerful tool, and it's something that we like to apply to this 2D Fermi gas. And then secondly, people are getting better and better at really shaping light into whatever kind of profile you like. And so by running this objective in reverse, you can actually send down very well-controlled, very intricately shaped optical potentials and control very well the environment that your atoms are living in. And so just to give an idea of how well we can shape light these days, this is a picture of my PhD advisor actually sculpted out of a laser beam. So this is a cut through the laser beam, and you can see it makes this nice face. And the type of physics that this is by no means an exhaustive list, but maybe it's exhausting, but it's not exhaustive. But some of the physics we might want to study would be, for example, turbulence in the system. So if you drive this 2D Fermi gas, for example, some short length scale, can we observe some kind of maybe inverse cascade of energy, which is something that people would be quite interested to see. Also, I think something that's interesting and something that people are discussing quite a bit is what's the interplay of sort of BCS physics, which requires fermions to somehow pair up before they can form a superfluid, with the BKT physics, which is more familiar from bosonic 2D systems. And so BKT physics sort of demands some kind of change in the topology of a system in order to go from a normal to a superfluid in 2 dimensions. And then thirdly, this is really the big drive of the machine, and the thing we're really pushing for is to try and get into a regime of rapidly rotating Fermi gases. And the reason we want to go to a regime of fast rotation is that simply due to the equivalence of the Lorentz and the Coriolis force, the physics of a neutral particle under rotation is really analogous to the physics of a charged particle in a magnetic field. And so if you can rapidly rotate these gases, you can really simulate the physics, for example, of electrons in a magnetic field. And so even though we're nearly 30 years after the sort of first achievement of BEC, and so cold atoms have been around for a while, this regime of observing Landau levels and seeing quantum Hall physics is something that still hasn't been achieved in cold gases. And so this is really the big push of what we're building this machine for. And so I'd just like to finish again by thanking the students. These guys I've already mentioned. This is Bishru, Parth, and Zenji. Elia and Cedric are 2 new grad students who are helping set up the new machine. Julian's just moved to Paris, and we're all under the supervision of Martin Zwilein. So with that, I'd like to finish and to thank you very much for your attention.
Okay, so I think, no, we have to move on because we are already